the applicability of healthcare facilities guidelines, specifically National Electrical Code Section 517, may not directly apply to an airport lighting system design. Airport lighting systems possess unique requirements and standards not specifically addressed in NEC 517. NEC 250.30 requires ground fault protection of equipment in certain locations, including electrical distribution systems. However, it does not provide specific guidance for airport lighting systems or generator-backed systems. NEC 520.22 addresses the use of ground fault circuit interrupters, or GFCIs, in commercial buildings, but it does not cover generator-backed systems. The National Electrical Code Handbook provides additional commentary and examples to help interpret the NEC. In Section 250.30, the NEC Handbook states, ground fault protection for personnel is not required for the output of an on-site generator when supplying a single-ended emergency system or where there is no exposed 120 volts single-phase receptacle outlet or where the output of the generator is solely for motor loads. FAA Advisory Circular AC 150/5000, 340.49d, titled Airport Lighting Design, Construction, and Maintenance, provides guidance for the design and maintenance of airport lighting systems, but it does not specifically address ground fault protection for generator-backed systems. Based on the available information, a conservative approach would be to follow the guidance in NEC 517.17, which prohibits ground fault protection between on-site generators and essential electrical system transfer switches feeding essential electrical system circuits. This suggests that ground fault protection should not be enabled on any circuit breakers between the emergency generator and the airport lighting system. To ensure reliability and safety, consider the following recommendations. Firstly, conduct a thorough risk assessment of the system to identify potential ground fault hazards. Secondly, install ground fault detection devices on feeders to monitor for ground faults without interrupting power. Thirdly, implement a comprehensive maintenance and testing program to verify the proper operation of the system. And fourthly, consult with a qualified electrical engineer specializing in airport lighting systems for specific design and safety recommendations. Ground fault protection is a critical safety measure designed to detect unintentional electrical faults to ground. These faults can occur when current flows through an unintended path, such as through a person or equipment casing, rather than the intended circuit. Ground fault protection systems typically employ devices that monitor the balance of current flowing through the circuit conductors. In a properly functioning circuit, the current flowing into the load should equal the current returning from the load. However, if a ground fault occurs, a portion of the current will divert through the unintended path, creating an imbalance that the ground fault protection device detects. When a ground fault is detected, the protection device quickly interrupts the circuit, minimizing the risk of electrical shock or equipment damage. Ground fault protection is particularly important in systems where there is a high risk of electrical shock, such as in wet or damp environments, or where sensitive electronic equipment is used. The National Electrical Code, or NEC, mandates ground fault protection in various applications to ensure the safety of personnel and equipment. The NEC provides detailed guidelines for the installation and application of ground fault protection devices, including specific requirements for different types of electrical systems and equipment. The NEC is a comprehensive set of standards that govern the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The NEC is developed by the National Fire Protection Association, or NFPA, and is widely adopted by state and local jurisdictions. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. Airport lighting systems are critical infrastructure that ensures the safe operation of aircraft during takeoff, landing, and taxiing. These systems include various types of lighting fixtures, such as runway edge lights, taxiway lights, approach lights, and beacon lights. Airport lighting systems must be designed and maintained to meet stringent performance requirements to ensure adequate visibility and guidance for pilots. The design of airport lighting systems is governed by various standards and regulations, including those issued by the Federal Aviation Administration, or FAA. The FAA provides guidance on the design, installation, and maintenance of airport lighting systems to ensure their safety and reliability. Emergency generators are essential components of critical infrastructure, providing backup power in the event of a utility power outage. These generators are typically used to power essential equipment and systems such as lighting, life support systems, and communication systems. Emergency generators must be designed and maintained to ensure their reliable operation during emergencies. The NEC provides specific requirements for the installation and operation of emergency generators, including requirements for automatic transfer switches, fuel supply systems, and ventilation systems. Automatic transfer switches, or ATSs, are used to automatically switch between the normal power source and the emergency power source in the event of a power outage. These switches are essential for ensuring the continuity of power to critical loads during emergencies. Automatic transfer switches must be designed and installed to meet specific performance requirements, including the ability to quickly and reliably transfer power between the two sources. A risk assessment is a systematic process of identifying and evaluating potential hazards and risks associated with a particular system or activity. Risk assessments are essential for identifying potential safety hazards and for developing appropriate mitigation measures. In the context of electrical systems, risk assessments can help identify potential ground fault hazards and other electrical safety risks. Ground fault detection devices, or GFDDs, are used to monitor for ground faults without interrupting power. These devices can provide early warning of ground faults, allowing for corrective action to be taken before a fault causes an outage or safety hazard. Ground fault detection devices are typically used in conjunction with ground fault protection devices to provide a comprehensive ground fault protection system. A maintenance and testing program is essential for ensuring the proper operation of electrical systems. Regular maintenance and testing can help identify potential problems before they lead to failures or safety hazards. Maintenance and testing programs should include regular inspections, testing of protective devices, and cleaning of equipment. Consulting with a qualified electrical engineer is essential for ensuring the safe and reliable design and operation of electrical systems. Electrical engineers have the knowledge and experience to design electrical systems that meet applicable codes and standards and to identify and mitigate potential safety hazards. Electrical engineers can also provide guidance on the selection, installation, and maintenance of electrical equipment. The conservative approach mentioned earlier suggests prioritizing the avoidance of nuisance tripping of ground fault protection, or GFP, devices during emergency generator operation, especially in critical applications like airport lighting. Nuisance tripping refers to the unwanted or unnecessary activation of a protective device, such as a circuit breaker, when there is no actual fault condition. In the context of airport lighting, nuisance tripping of GFP could lead to a loss of lighting, which could have serious safety consequences for aircraft operations. The reasoning behind considering disabling GFP in certain situations is that the generator's grounding system might interact with the existing grounding system in a way that creates a false ground fault signal. Generators, particularly portable or temporary ones, may have different grounding configurations compared to the utility power system. This difference can sometimes lead to circulating currents in the ground conductors, which the GFP device might misinterpret as a ground fault. However, disabling GFP should not be done lightly. It should only be considered after a thorough risk assessment and with the involvement of qualified electrical engineers who can carefully evaluate the potential consequences. Alternative solutions, such as adjusting the GFP settings or using ground fault detection devices, should be explored first. Ground fault detection devices, or GFDDs, offer an alternative approach to ground fault protection. Unlike GFP devices that interrupt the circuit where ground fault is detected, GFDDs provide an early warning of ground faults without causing an outage. GFDDs can be used to monitor for ground faults and alert maintenance personnel to investigate and correct the problem before it leads to a more serious issue. This approach can improve the reliability of the electrical system while still providing a level of ground fault protection. Selective coordination is another important consideration in ground fault protection design. Selective coordination refers to the practice of coordinating the tripping characteristics of different protective devices in a way that ensures that only the device closest to the fault will trip, while other devices upstream remain unaffected. This helps to minimize the extent of the outage and to isolate the fault quickly. In airport lighting systems, selective coordination is particularly important to ensure that a ground fault in one lighting circuit does not cause a widespread outage that affects other critical lighting circuits. The voltage level of the electrical system also plays a role in ground fault protection design. Higher voltage systems, such as 480/277 volts, typically require more sophisticated ground fault protection systems compared to lower voltage systems, such as 120/240 volts. This is because higher voltage systems have a greater potential for ground faults to cause significant damage or injury. The impedance of the grounding system is another important factor to consider. The grounding impedance affects the magnitude of the ground fault current and the sensitivity of the ground fault protection system. A low impedance grounding system will result in a higher ground fault current, which can make it easier for the GFP device to detect the fault. However, a low impedance grounding system can also increase the risk of equipment damage during a ground fault. A high impedance grounding system will result in a lower ground fault current, which can reduce the risk of equipment damage but also make it more difficult for the GFP device to detect the fault. The type of load being served by the electrical system also affects the ground fault protection requirements. Some loads, such as motors and transformers, can generate harmonics that can interfere with the operation of ground fault protection devices. In these cases, special GFP devices that are designed to filter out harmonics may be required. The location of the electrical equipment is another factor to consider. Equipment located in wet or damp environments is more susceptible to ground faults and may require more stringent ground fault protection measures. The age and condition of the electrical equipment can also affect its susceptibility to ground faults. Older equipment may have insulation that is degraded or damaged, which can increase the risk of ground faults. Regular inspections and maintenance can help to identify and correct potential problems before they lead to ground faults. The availability of qualified personnel to maintain and test the ground fault protection system is also an important consideration. Ground fault protection systems should be inspected and tested regularly to ensure that they are operating properly. This requires trained personnel who have the knowledge and experience to perform these tasks. The cost of the ground fault protection system is another factor to consider. Ground fault protection systems can range in cost from relatively inexpensive to quite expensive, depending on the complexity of the system and the features that are included. The cost of the ground fault protection system should be weighed against the benefits of the system in terms of safety and reliability. The potential consequences of a ground fault should also be considered. In some cases, a ground fault can result in significant damage to equipment or injury to personnel. In other cases, the consequences may be less severe. The potential consequences of a ground fault should be considered when determining the appropriate level of ground fault protection. The overall goal of ground fault protection is to provide a safe and reliable electrical system that protects personnel and equipment from the hazards of ground faults. This requires careful consideration of all of the factors mentioned above and a commitment to regular inspection and maintenance. The specific requirements for ground fault protection can vary depending on the application and the jurisdiction. It is important to consult with qualified electrical engineers and to follow applicable codes and standards to ensure that the ground fault protection system is properly designed and installed. In the context of airport lighting systems, the FAA provides guidance on the design, installation, and maintenance of these systems. This guidance should be followed to ensure that the lighting systems are safe and reliable. The NEC also provides specific requirements for airport lighting systems, including requirements for ground fault protection. These requirements should be followed to ensure that the electrical systems are safe and compliant. In addition to the FAA and NEC requirements, local codes and regulations may also apply. It is important to check with the local authorities to determine the specific requirements for ground fault protection in the area. The design and installation of ground fault protection systems should be performed by qualified electrical engineers and electricians who have the knowledge and experience to perform these tasks safely and effectively. The selection of ground fault protection equipment should be based on a careful evaluation of the specific requirements of the application. The equipment should be of high quality and should be designed to meet the applicable codes and standards. The installation of ground fault protection equipment should be performed in accordance with the manufacturer's instructions and the applicable codes and standards. The ground fault protection system should be tested after installation to ensure that it is operating properly. Regular inspections and maintenance should be performed to ensure that the ground fault protection system continues to operate properly over time. The records of inspections, testing, and maintenance should be maintained for future reference. The training of personnel who will be working on or around the electrical system is essential for ensuring their safety. Personnel should be trained to recognize potential hazards and to follow safe work practices. Personnel should also be trained on the proper operation and maintenance of the ground fault protection system. The coordination of ground fault protection with other protective devices in the electrical system is important to ensure that the system operates properly during a fault. The coordination study should be performed by a qualified electrical engineer. The documentation of the ground fault protection system is essential for ensuring that the system can be properly maintained and repaired. The documentation should include a description of the system, the location of the equipment, the settings of the protective devices, and the results of testing and maintenance. The communication of ground fault protection information to all stakeholders is important to ensure that everyone is aware of the system and its purpose. The stakeholders include the owners, operators, maintainers, and users of the electrical system. The continuous improvement of the ground fault protection system is important to ensure that it remains effective over time. The system should be reviewed periodically to identify areas where improvements can be made. The goal of continuous improvement is to provide a safer and more reliable electrical system. Understanding the principles of ground fault protection is essential for electrical engineers and electricians. This knowledge is necessary for designing, installing, maintaining, and troubleshooting ground fault protection systems. The NEC provides a wealth of information on ground fault protection. This information should be consulted when designing, installing, maintaining, and troubleshooting ground fault protection systems. The FAA also provides guidance on ground fault protection for airport lighting systems. This guidance should be followed when designing, installing, maintaining, and troubleshooting ground fault protection systems for airport lighting systems. Consulting with qualified electrical engineers is essential for ensuring that the ground fault protection system is properly designed and installed. Electrical engineers have the knowledge and experience to design electrical systems that meet applicable codes and standards and to identify and mitigate potential safety hazards. The use of ground fault protection devices is not a substitute for safe work practices. Safe work practices should always be followed when working on or around electrical equipment. The wearing of personal protective equipment, or PPE, is essential for protecting personnel from electrical hazards. PPE should include items such as safety glasses, gloves, and insulated clothing. The de-energizing of electrical equipment before working on it is essential for preventing electrical shock. The lockout, tagout, or LOTO procedure should be followed when de-energizing electrical equipment. The use of proper tools and equipment is essential for working safely on electrical equipment. The tools and equipment should be in good condition and should be appropriate for the task. The maintaining of a clean and organized work area is essential for preventing accidents. The reporting of any electrical hazards to the appropriate personnel is essential for preventing injuries. The continuous learning about electrical safety is essential for staying up to date on the latest safety practices. The participation in safety training programs is essential for improving electrical safety knowledge and skills. The promotion of a culture of safety is essential for creating a safe work environment. A culture of safety is one in which safety is valued and prioritized by all employees. The continuous monitoring of the electrical system for potential problems is essential for preventing accidents. The use of technology to monitor the electrical system can help to identify potential problems early on. The prompt response to any electrical problems is essential for preventing accidents. The prompt response should include the investigation of the problem and the implementation of corrective actions. The continuous evaluation of the effectiveness of the electrical safety program is essential for ensuring that the program is meeting its goals. The evaluation should include the review of accident data, the feedback from employees, and the results of audits. The adaptation of the electrical safety program to changing conditions is essential for ensuring that the program remains effective over time. The changing conditions may include changes in technology, changes in regulations, and changes in the work environment. The commitment to electrical safety by all stakeholders is essential for creating a safe work environment. The stakeholders include the owners, operators, maintainers, and users of the electrical system.